Your Academic Skills Center presents this video series to help you strengthen your statistics skills.
Hello STAT students, and welcome to the Multiple Linear Regression and Diagnostic Statistics video presentation. My name is Janine Allwright, and I am the Instructional Specialist at Walden's Academic Skills Center, where I lead the Statistics Tutoring team. In this video presentation, we will once again engage with the multiple linear regression, but this time for the purpose of diagnostic statistics, also known as testing assumptions. Once again, I'm going to remind you that we are working with a limited sample data set to answer a question about the greater population, and that we're using the multiple linear regression test as the inferential test of choice. I will explain why it's important to test the model, and I will spend detailed time on the summary of the assumptions. I will offer an example of a multiple linear regression model in SPSS that includes dummy variables as well. And I will deliver a full interpretation as we know it at model level, variable level, and at the diagnostic statistics level as well. I will be sure in that interpretation to tell the full story of the data. Now let's get started. The figure on the next screen is going to look familiar to you if you have watched previous videos in this series, because this is how I show that we are working with a limited sample data set to answer a question about the greater population, and we use inferential statistics to get from that sample information to that population outcome. The inferential statistics test of choice for this presentation is multiple linear regression. It lies firmly on the right side of our screen between the inferential statistics and the population arrow, and we will run the diagnostic statistics on that model. Before I engage you with the list of assumptions that we're going to test in this video presentation, I want to share with you where I learned my knowledge about the diagnostic statistics. Here is a reference list of my two favorite stats books, the Field book and the Tabanic and Fidel book. Not only do these authors describe these assumptions very well, they also offer solutions in case you break an assumption. I assume that you have your own list of references in your classroom or outside, but feel free to evaluate these books as well. I will be sure to add these titles and authors in the transcript that goes with this video. And here is the list of the assumptions that we are going to test. We're going to start with what Field calls beast of bias, and those are the outliers. We're going to evaluate if there is autocorrelation. Moreover, we're hoping for lack of autocorrelation, which really means that the errors are independent. We do not hope that the independent variables have a perfect relationship with each other, because that would indicate multicollinearity. We're going to evaluate if the errors are normally distributed. And we do not want to see a non-constant error variance, also known as heteroscedasticity. We are aiming for Homo Statisticity. And we will evaluate the linear relationships that is a basic assumption of every regression model. Let's take a moment to understand why testing of assumptions and the diagnosis of our model is important. The bias or any other violations of assumptions will influence how well our model predicts. Remember that we are here to estimate parameters. We are using our limited sample data set to estimate the model for the greater population. If we break assumptions, then the model is not properly generalizing across the greater population. We use the mean, for instance, to calculate the sum of squared errors. That is also used to calculate the standard deviation, which is also used to estimate the standard error, which is used to calculate a confidence interval. If the sum of square errors is biased, then all those test statistics that are based on the sum of squares will also be biased. Keep in mind that a lot of our parameters that we estimate exist within a confidence interval. For instance, the unstandardized beta, But if we break assumptions, if we violate these assumptions, then we can be off. When assumptions are met, then we can trust on average that the regression model from the sample can stand in for the greater population. Of course, it's always possible that there are issues with the population model beyond the assumptions, but the likelihood that the sample and the population model are the same increases when assumptions are met. Let's talk about the outliers, or as Field calls it, the beast of bias, and that is for a reason. It truly is a problem to have an outlier, and even one outlier can bias your model. It truly is that value that lies outside of the rest of the data. It's that score that is very different from the rest of the data. And as I mentioned earlier, it can bias your parameter estimates, but also most test statistics are based on the sum of squares. And so the sum of squares will be biased by your outliers that will then bias your test statistics as well. Now, as the outlier is that score that substantially differs from the trend of the data, we're going to use Cook's data to find those errors. But I sometimes hear students say, well, just delete the outliers. It's not a good idea because that in itself is its own bias, right? You're not really telling the true story of the data if you start deleting outliers. And furthermore, if you delete a first round of outliers, I can guarantee you that the next round will pop up. So we will use Cook's distance, and it's meant to find the errors. We're looking for large differences between the trend and what is outside of that trend, and Cook's is supposed to come out between 0 and 1. So it's the measure of the overall influence of a case on the model. Greater than 1 is a measure of concern. But even if Cook's comes out smaller than 1, don't delete those outliers. You still should be interested in figuring out what that outlier means. In essence, the Cook's distance will find these influential outliers in a set of predictor variables. It is a way to identify these points that negatively affect your regression model. And that takes me to the second assumption here, lack of autocorrelation, also known as independence of errors. And what we are aiming for is that the errors are not correlated, so that the residuals are totally independent of each other for any two observations. If we break this, the confidence interval and the significance will be invalid. Now, the lack of autocorrelation test was developed by Durbin and Watson, and hence the name, and that tests whether these adjacent residuals are correlated. In the original published article, the Durbin-Watson was held to a more conservative rule between 1 and 3, but more recent statistics research shows that even around 2, you might have a problem, depending on sample and model. Let's move to our next assumption in our conversation about the diagnostics of the model, and that is the multicollinearity. If you have viewed other videos in this series, then you've heard me talk about those relationships. Usually when I evaluate the correlation matrix, I'm not just looking at the health of the relationships between the predictor variables and the dependent variable. I'm also evaluating if the independent variables have significant relationships with each other. And you now know that I usually put up a tiny little red flag. If that happens, it might be a point to return to if I find issues with the model in my later interpretation. But the relationships between those independent variables is not a black and white situation. You will always find somewhat of a relationship between those variables, in the same way that you will hardly ever find a perfect correlation of a correlation coefficient of 1 between those variables. It's a matter of evaluating if that relationship between the independent variables really influences the quality of your model. Because it's important to know how these independent variables are correlated. If you have too much correlation there, you are going to end up with untrustworthy betas. As your collinearity increases, so do the standard errors of that beta coefficient. So you could be overstating there in your model. The other problem that arises is that if you have collinearity, you're limiting the size of your R, really. Remember that R is the measure of the correlation between the independent variables of the outcome and the observed values, and that your R square indicates that variance of your dependent variable for which that model accounts, right? The combination of those independent variables. You could be understating that. It's also a matter of the predictor importance. It's hard to evaluate which predictor truly brings more to your model when you have multicollinearity. And for us, that is important because of the social change question. There are several methods that you could use to evaluate that relationship between those independent variables. And I've already mentioned the correlation matrix. While that is a good ballpark method, it will miss more subtle forms of multicollinearity. So for our multicollinearity analysis, we're going to trust the variance inflation factor. And the ballpark figure there is that the largest VIF should not be greater than 10. If you get a number there that is greater than 10, then it truly is an item for concern. You could also look at the average of the variance inflation factors. If you have anything substantially greater than 1, then maybe you have some bias there. Sometimes you also see the tolerance factor there. The tolerance below 0.1 indicates a problem, or you could also view it as a tolerance. Anything below 0.2 might be a potential problem. But again, we're going to focus on the VIF, the variance inflation factor, and we hope that that is smaller than 10. The next item on our assumption list is that we hope for errors that are normally distributed, with a residual around the mean of 1. And the reason why we hope for that is that we do not want that distance between the model and our observed data. And if we find a difference, that it's only an occasional occurrence. Please do not confuse this with the predictor having to be normally distributed. That is not the same. In small samples, a lack of normality of these errors will invalidate the confidence interval and the significance test. In large samples, that won't matter because the central limit theorem is at work. If you fail this assumption, you could argue that you can bootstrap, that is using the sample as if it is a population and you keep sampling from it. You then keep calculating the parameter with each bootstrapped sample and you can graph that out, thereby mimicking the sample process. We're going to evaluate the errors by asking SPSS to give us that histogram that will show us whether those errors are normally distributed. The next item on our list is linearity, and that is the linearity of the relationship between predicted dependent variable scores and errors of prediction. We hope to assume that because if you have non-linearity or failure of linearity, it doesn't necessarily invalidate the analysis, but it weakens the model. We evaluate that linearity with a scatter plot, and if we see our scatter and it has a random scatter, then we can assume that linearity is fulfilled. The last item on our list is that non-constant error variance, that Homo Statisticity. And what that really is the assumption that the standard deviations of the error of prediction are approximately equal for all predicted DV scores. It's a problem when you don't have that, and you will see that in the scatter plot because you will have some kind of pattern there. We usually ask for a scatter plot between the predicted z-scores on the x-axis and the residual z-scores on the y-axis, and I will remind you to put a fit line in there so that it's easier to see these patterns. If you don't see a pattern, then your Homo Statisticity is fulfilled. And that completes our rather detailed explanation on what all the assumptions mean and why they are a problem and how we are going to test them in SPSS. Having said that, it's time to move to our multiple linear regression model so that we can practice this. And as you can see here, I have a research question on the screen. It's very similar to what I used in a previous video, except that I swapped out that categorical variable now with a new variable, professor type, and I will introduce that to you in a moment. But you can see here that I'm asking whether grant funding, committee work, and the professor type will affect the number of publications in higher ed. Of course, I've translated that into two hypotheses. The alternative hypothesis is stating what I'm hoping to find, and the null hypothesis denies that. So the setup of this multiple linear regression will show two independent variables at our scale. a third independent variable that is categorical, and a dependent variable that is scale. And we're going to follow our usual interpretation. We're going to look at model level first, followed by variable level, and of course then we will engage with the diagnostic statistics. With a bit more detail at model level, we are not going to look at the correlations this time because we are evaluating the multicollinearity anyway in the model diagnostic, and that trumps that method of the correlations. So we will just look at the significance of the model, followed by the adjusted R-square in the effect size. And we will then move to the interpretation at the variable level. We will evaluate the significance of each variable, the unstandardized beta. We will evaluate the dummy variables and interpret them, and we will talk about the standardized beta. Lastly, we will add that diagnostic statistics to our conversation. And I have the data set on the screen here that you are now familiar with if you've watched previous videos. This is a simulated data set that I've created for the purpose of this presentation, and it measures the number of publications, grant funding, and committee work. And for this presentation, I have a new variable called college professors. I've already ran the descriptive on this variable. I have 3 levels in this variable. Either a professor is a research scientist, more focused on research, or the professor is a teaching mogul focused on teaching, or a professor works in leadership and higher ed. We can see here that this was coded for the purpose of dummy coding in the direction of the leadership. Leadership is the reference category here. So I have created 2 new variables, one called research scientist and the other one teaching mogul. And I can now set this up in the regression. Let's start with clicking the Analyze button and bringing up that regression option, linear. I'm going to bring my dependent variable number of publications over in the dependent box. Grant funding and committee work will both make a presence in this regression model. And here come my 2 new dummy variables, research scientist and teaching mogul. I'm going to click the options here, and first I'm going to click the descriptive statistics because discussing how your variables act in that sample data set is Stats 101, but now I want to click for all my assumptions. I'm clicking for my collinearity diagnostic. I need my Durbin-Watson. Click continue. I'm going to ask for my plots. This is a crisscross applesauce situation between my z-pred and my c-residual. In other words, I'm going to put the predicted z-score on the y-axis and the residual z-score on the x-axis, and I'm going to ask for a histogram. And under the Save button, I will definitely ask for those standardized residuals and the Cook's distance. And that completes the setup of our model diagnostics here. So let's click OK to generate the regression output. And here we are. Here is our output on the screen. And we start, as always, by describing our variables to tell our reader how they act in this sample data set. I can describe my number of publications, grant funding, and committee work with mean, standard deviation as sample size. But I can't describe my research scientist and teaching mogul here because these groups are in a dummy coded state. So I'm going to reach back to the descriptive box here, the frequency distribution for the original categorical variable, and I can now use those frequencies for research scientist, teaching mogul, and leadership. Even though I'm not going to describe the correlations here because our multicollinearity diagnostic will trump that, I still received the output because I asked for the descriptive statistics, but I'm moving to my interpretation at model level. Our model is significant, p smaller than 0.05, and I have a nice adjusted R-squared. 21.8% of the variance of the number of publications is explained by the combination of our professor type, grant funding, and committee work. Let's move to the interpretation at model level here. I have to evaluate my significance first for every variable, and everything is significant here, even committee work. And I know that if grant funding goes up with $10,000, my dependent variable goes up with 0.978 publications while holding the other variables constant. If committee work goes up with 1 unit, my number of publications drops with 0.741 publications while holding the other variables constant. And the interpretation of my dummy variables here is going to be compared to that reference category, the leadership. So research scientists compared to instructors who work in leadership is 4.252 lower in publications while holding the other variables constant. And a teaching mogul is actually producing less publications compared to the leadership professor, minus 5.46. In order to compare these variables for the power that they bring to that dependent variable, I want to use the standardized coefficients because I want to take that unit effect out of it, and I can see here that grant funding delivers that positive message to your number of publications. It drives it in a positive way. On the negative side, being a research scientist doesn't work as negatively as the teaching mogul does. Truly, the teaching mogul is the one who delivers the lowest number of publications. Now let's get started with our interpretation of the model diagnostic. I usually work my model diagnostics from the top down, so I'm starting with the Durbin-Watson here. It is in that model box if you're looking for it. It lives in that model summary, and that measures whether we have that independence of errors, right? Lack of autocorrelation. So I want to avoid that correlation between the residuals, and for that purpose, the Durbin-Watson hopefully lands somewhere between 1 and 3, but keep in mind that I mentioned that even around the number 2, it's still a little bit troublesome. Luckily for us, I have a Durbin-Watson of 0.502, so no problem here. Let's move on to our variance inflation factor. That is that factor that measures the multicollinearity. I mentioned that that value has to be under 10. The highest one ought to be under 10, and that is indeed the case. I can also look at the tolerance. They're really nicely close to 1, which is really great. They're not near 0.1 or 0.2, as I mentioned earlier, so assumption fulfilled. Thirdly, I'm going to bring up the Cook's distance, and I want to look at the distance in that essence. You want to calculate the difference between the minimum and the maximum. And that value has to be smaller than 1, so there's no problem with our outliers here. That assumption is also fulfilled. Let's move on to our charts, and I can see here that I have a nice histogram to represent the normal distribution of the errors of the residuals here. Surely I have a bit of a tail here on the right side, but nothing to concern myself with. This is truly normal enough to me. And then lastly, I'm going to evaluate the scatter plot. The first thing I want to mention here is that this looks like a random scatter. I have a little bit of heaviness here at the bottom, but again, nothing to concern myself with. So I'm going to check off the linearity assumption. And to evaluate the Homo Statisticity, I'm going to double click in this graph. I'm going to bring up that fit line. The only purpose for putting that fit line in there is to really make it easier for yourself to see any pattern. I don't really see anything here. I don't see a funnel or a trumpet or anything like that. So I'm going to sign off on that assumption of Homo Statisticity. It is fulfilled. And with that, all our assumptions are fulfilled, and that leaves me only one more task here. I'm going to take you back to the PowerPoint to show you what these assumptions look like when I just bring them up as tables in my presentation, and we'll evaluate the assumptions here once more. The Durbin-Watson is going to evaluate if I have independence of errors, and I surely do because that value lies safely between 1 and 3 and not even near the number 2. I do not have any issues with my variance inflation factor. In that essence, I did not see any sign of multicollinearity that is disturbing this model in any way. The Cook's distance is healthy, it's below 1, so that indicates that I have no undue influence of outliers in this model. My histogram of the standardized residuals looked nice. And the scatter plot looked healthy for its scatter, so linearity is fulfilled, and I see no pattern. Even after I place that fit line in there, I do not see any patterns here that might disturb the model. So Homo Statisticity is fulfilled. And that completes the presentation, but I do want to mention one more thing. I want to show you the references again. If you are interested in learning more about the details of this diagnostic statistics, then please feel free to find these books. You can try in our library, as we have books here at Walden as well. Or alternatively, if you're interested in engaging with a quantitative methodology, that might be a nice investment. And with that, our multiple linear regression presentation with a full diagnostic statistics has now completed.
Thank you for watching this video presentation. If you have course-level statistics questions, reach out to our stats tutors at statsupport@mail.waldenu.edu or view our statistics support resources at academicskills.waldenu.edu.